All right, so this is video 16 for the Bailey Real Analysis series. And in this video, we'll just go into introduction to series. And we're familiar with series from calculus course. And so a series is an infinite sum of the term, where the terms of the series are an plus a2 plus a3 and so forth. So the sequence an, the terms of that sequence, you're adding those terms together to make the infinite series. Now the question is, how do you find the sum? And you do this by finding a sequence of what's called the nth partial sums. So let S1 be the first term of the sequence an, so S1 is A1. S2 be the sum of the first two terms of the sequence an, so that's A1 plus A2. And then S3 is the sum of the first three terms of the sequence an, so A1 plus A2 plus A3, and you continue this process, and so Sn is the sum of the first n terms of the sequence an. So you can form a sequence out of this, and that sequence is called the nth partial sums. Now we answered if the series converges if and only if this sequence of nth partial sums converges. That is, if the sequence Sn converges to some value s, then the series itself an is equal to s. Okay, and I'm going to go through several tests and theorems involving these series, and these should be theorems that we're familiar with, and then at the end go through some examples. The first one is the nth term test. And the nth term test says if a series converges, then its nth term, or the sequence an converges to 0. All right, but the converse is not true. It is not true that if the sequence an converges to 0, that the series consisting of the sequence converges. So for instance, we know 1 over n converges to 0, but we'll do later on that the series 1 over n diverges. And that's actually called the harmonic series. All right, so the converse isn't true. But the contrapositive, since its logical equivalent, would be if the sequence does not converge to 0, then the series an diverges. Okay, so contrapositive of the statement of if the series converges, then the sequence an converges to 0. Then if an does not converge to 0, then the series diverges. And that's actually called the nth term test for divergence, the quick test you can run to see if you're given a series and whether it diverges or converges. All right, so we talked about Cauchy sequences, and there's also a Cauchy criterion for series. And the series converges if and only if for all epsilon greater than 0, there exists a capital N, such that for all little m bigger than little n, which is bigger than capital N, we have that the absolute value of the terms an plus 1, an plus 2, ... up to an plus am is less than epsilon. Okay, so the reason why we have it like that is where we have m greater than n greater than capital N is we want to do without loss of generality. So further, we know that Cauchy for a sequence just means for all epsilon there exists a capital N. For all little n and m bigger than capital N, we have the absolute value of the difference am minus an to be less than epsilon. So that's what it means for a sequence to be Cauchy. So for our sequence of partial sums, so we look at the sequence of partial sums and apply this Cauchy definition for convergence criterion for a sequence. In this case, our sequence is the nth partial sums. And so that's why there'll be for all little n and m bigger than capital N, we have S subscript m minus S subscript little m is less than epsilon. And what does it look like? So the nth term of the, or Sm, that's equal to a1 plus a2 dot 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 plus am, which you can write it as a finite series with a summation from I equals 1 to m. The nth term is basically the same thing. It's just a1 plus a2 up to plus an, which you can write as a finite series or finite sum from I equals 1 to n. All right, and so without loss of generality, we're going to assume the index m is going to be greater than n, and then n's going to, obviously n's going to be greater than our cutoff point, capital N. So when we take the difference in this case of S subscript m minus the nth term Sn, we're subtracting out, so a1 plus a2 dot 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 up to am. So this is our Sm, and then we're subtracting out Sn. And since m is bigger than n, there's some cutoff. So there's some point where I have these values that are not in Sn, because these all have indices bigger than n. But since it does consist of Sn and then added onto that some finite amount of terms beyond that Sn, you subtract out Sn, and that leaves you just with this, the terms an plus 1, an plus 2 dot 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 up to plus am. Said, written as sums, you could say that the sum from I equals 1 to m of ai minus the sum from I equals 1 to n of ai is equal to the sum from I equals n plus 1 to m of ai. And again, this is when we're going to use, assuming without loss of generality, m is greater than n, greater than capital N. All right, that's where this part comes from. All right, that is our Sm minus Sn. Okay, so that's Cauchy Criterion for series. So I'm gonna go over a proof of the nth term test. And the nth term test is that the series, if an converges, then the sequence if the series converges, then the sequence it consists of an converges to 0. So assume the series converges. Let's call it sum S. So the sequence of nth partial sums converges to S. Then we know Sn is equal to a1 plus a2 dot 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 plus a subscript n minus 1 plus an. And then n minus 1, S subscript n minus 1, that's the same thing. It's just all the way up to plus a n minus 1. So they share all of the terms except for the last term an. So when we subtract Sn minus 1, everything cancels out. Subtracting this from that, that from that, everything cancels out, and we're left with an. Okay, so we know the sequence of nth partial sums converges. So if we take the limit of Sn minus 1, we can break that up. So it's the limit of the limit of each one, and the limit of each one is S, since we know Sn converges to S. So we have S minus S, which is 0. All right, and thus we have that this is also 0, since the limit of the difference of the Sn minus 1 is 0. Because this was S minus S, which was 0. So that's the proof of the nth term test. A geometric series, that's a particular type of series of the form from k equals 0 to infinity. So here with the geometric series, we start with index 0, and it's a times r to the k, where a is some real number, and it's equal to a plus ar plus ar squared plus dot dot dot. So our index is corresponding to the exponent that goes with the value r. Now this thing either converges or diverges. It's going to converge, and it actually, we know what the sum is when it converges. Its sum is a over 1 minus r if the absolute value of r is less than 1, provided that a is not 0. Diverges if the absolute value of r is greater than or equal to 1. So for the proof, as far as we're going to show, and this is just a shorthand proof of that, it converges to a over 1 minus r if the absolute value of r is less than 1. And it's a clever proof, so we can look at the nth partial sum. So that's a plus ar squared plus dot dot plus ar to the n. If we multiply this by r, we're multiplying each of these a's by r, so that a becomes ar becomes ar squared becomes ar cubed, and then ar to the n becomes ar to the n plus 1. Then if we were to subtract them, so if we do Sn minus r times Sn, you'll see what cancels out. So we have the ARs would cancel out, the AR squares cancel out, and then AR cubed, and you'll see that AR to the n would cancel out with an AR to the n down here, and so you're left with just A plus AR, or minus, right, because we're subtracting, so it'd be A minus AR to the n plus 1. So that's what you get when you subtract the nth partial sum Sn minus r times that nth partial sum. So we can write this as, so we have Sn equal to, so we could factor out Sn. Okay, so that gives us Sn times 1 minus r equal to a minus ar to the n plus 1. Then divide both sides by 1 minus r. So then you get Sn equal to a minus ar to the n plus 1 divided by 1 minus r. Okay, so then from there, you can break it up as two fractions with the same denominator of 1 minus r. So you have a over 1 minus r minus ar to the n plus 1 over 1 minus r. They share a in common, so factor out a. So that's 1 over 1 minus r. Then minus r to the n plus 1 to the 1 minus r. All right, so that's what we get. And again, all of this is equal to Sn. So now if it converges, that means the sequence of the nth partial sum converges. So if we take the limit, right, we get limit of Sn is equal to the limit of everything on the right. Which you could factor out a, so that's equal to a. And limit of 1 over 1 minus r, since that doesn't involve anything within, that's going to be a over 1 minus r. Then minus the limit of r to the n plus 1 over 1 minus r. And then for r being between 0 and 1, the limit of r to the n is equal to 0. So this converges to 0. So the whole thing converges to 0. So that's why you get a over 1 minus r. And that's the limit of the nth partial sum. And this condition that we have r between 0 and 1, that means the absolute value of r is less than 1. So we proved that the geometric series converges for absolute value of r less than 1, and it converges to a over 1 minus r. And so this is like a sloppy proof, but figured out, and I went ahead and I did it all in blue, but I figured I'd go ahead and describe it. But that's the proof for that. The comparison test, now if you recall from calculus course, you can use the comparison test, and for the comparison test, you have two sequences, an and bn. Then there exists some capital N, so that for all little n bigger than capital N, we have 0 is less than or equal to an, which is less than or equal to bn. And so I think of if the sequence with the terms, once I get off to that cutoff point, so in this case, bn is bigger than an, so if bn converges, the series of bn converges, and the series of an converges. Since an is less than bn, then if the series of an converges, then or diverges, then the series bn diverges. Now notice that this is the contrapositive of this one, right? Because if the series bn converges implies that series an converges, it follows that by contraposition, the series an diverges implies the series bn diverges. So for the proof of the comparison test, I just show the first case. Or you could show the second case and then say by contraposition you have the other one. So for the proof, I just need to prove that bn converges implies an converges. And here's the proof. So let Sn represent the nth partial sum, a1 plus a2 to ... plus an. Let Tn represent the nth partial sum, b1 plus b2 plus ... plus bn. So we know the series bn converges. So therefore its sequence of nth partial sums Tn converges. So we're going to show that the series an converges, and in order to do that, we need to show that this sequence of nth partial sums Sn converges. Well, by Cauchy criterion for sequences, if a sequence is Cauchy, then it converges. All right, if and only if it converges. So to show that the sequence of nth partial sums Sn converges, we can just show that it's Cauchy. All right. So that's how I do it. And so we're given some epsilon, given any epsilon greater than 0, we need to show that in order for this to be Cauchy, we need that the absolute value of Sm minus Sn, which is equal to a subscript n plus 1 plus a subscript n plus 2 plus dot dot plus a subscript m, the absolute value of that less than epsilon. And that was when we assumed the indices as far as little m bigger than little n, which is bigger than our cutoff index, capital N. That's what we need to show. All right, so what we know, well, our assumptions here, we know that this is true for some index n. So let's say that's index n1. So we know for all little n bigger than n1, we have a less than or equal to an, less than or equal to bn, for n1 is some natural number. We know the sequence Tn converges because that's the nth partial sum for the series of Bn. And since that converges, it's Cauchy. And so that means there's some n2, so that for all little m bigger than n capital N2, we have the Tm minus Tn, which is equal to Bn plus 1 plus Bn plus 2 and so forth to Bm. That's less than epsilon. We know that since Tn converges and it's Cauchy. So I just find n2 so that we have this condition for it to be Cauchy. So between n1 and n2, we're going to choose the maximum of the two, so that for all little m bigger than n, bigger than capital N, then our Sm minus Sn, which is equal to an plus 1 plus an plus 2 dot 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 plus am, that absolute value is less than the absolute values involving the b's, because we know for all n bigger than some particular n, we have that an is less than or equal to bn. And so an plus 1 is going to be less than or equal to bn plus 1, an plus 2 less than or equal to bn plus 2. So the sum of all of these is going to be less than the sum of the other ones. So therefore, and we know this is less than epsilon. So therefore, we've proved that it's Cauchy. Our nth partial sum Sn is Cauchy since we've had it to be less than epsilon. All right, thus we proved the series Bn converges implies the series An converges. So by contraposition, the series An diverges implies the series Bn diverges. Okay. Note that this condition where you have 0 less than or equal to an less than or equal to bn holds for all but finitely many terms. So this is why we need this sort of cutoff capital N value, so that for all little n bigger than capital N, we have that condition. It's not going to be true for the finitely many terms that come before that cutoff value. All right, so that is a proof of the comparison test. Here's the limit comparison test. If you have, again, two sequences, an and bn, and we require them to be strictly positive, then the limit of the quotient an divided by bn, if that equals some real number L, then we have that 1. If the limit is bigger than 0, then the series an converges if and only if the series bn converges. All right, so it's strictly positive, so I would assume the limit is going to be greater than or equal to 0. The second thing is that if we have the limit L equals 0, then the convergence of the series Bn implies the convergence of An series. All right, so to prove this, what are we going to assume here? So we're going to know, so An and Bn are positive. we also have that we're assuming that limit n goes to infinity of an divided by bn equals L. So based on that, that's if and only if for all epsilon bigger than 0, there exists some cutoff index capital N, so that for all little n bigger than capital N, we have the absolute value of the difference an divided by bn minus L to be less than epsilon. So that's true for any epsilon. All right, so since that's true for any epsilon, and we are also assuming if L is greater than 0. So if L is greater than 0, that's a real number greater than 0. Let's pick, then L over 2 is also greater than 0. I'm going to pick epsilon to be L over 2, or 1/2 L. Okay, so then that means I have that an over bn minus L, that's less than L over 2, which is if and only if negative L over 2 is less than an over bn minus L less than L over 2. So then I add L. So L plus negative L over 2 is L over 2. So I have L over 2 less than an over bn. And then L plus L over 2 is 3L over 2. All right, so I have those, and we know L over 2, that's less than 0. So I'm kind of already doing the proof that I've already written here, but I drew a visual. I don't know, maybe it kind of helps that we have our limit L, and we're, some epsilon above, some epsilon below. That epsilon is L over 2, or 1/2 L. Okay, so this is going to come in handy, and we can multiply by bn. So we have that 0 is less than L over 2 times bn less than an less than 3L over 2 bn. All right, so I'm going to use this inequality. And let's see, so we're going to first assume, so if an converges and bn converges as far as the series, and then also if the series bn converges and the series an converges is what we need to show. So to show so CONV for converges if and only if bn converges. All right, so let's see, what can we do? I'll try to use some kind of comparison tests. For the comparison test, what do we need for that? For convergence. So we're going to try to use this part of the comparison test. So the series bn converges implies a series an converges if we have this condition. So as long as the sequence, in this case bn, has terms that are bigger than are equal to the sequence from AN at this certain cutoff value, then if the series BN converges, that implies the series AN converges. Okay, so that's what we'll show. So I'll just write that comparison test for convergence. And I'll use different letters. So if you have that 0 less than or equal to xn, let's say less than or equal to yn, then the series yn converges implies that the series xn converges. All right, so note that this is bigger than that. So if the series 3L over 2 times Bn converges, that means that we have 3L over 2 times the series Bn converges, which means the series Bn converges. And note that because of, since we have 0 less than an less than 3L over 2 times Bn, and these are technically if and only ifs. So if and only ifs. Okay, then we have that the convergence of, in this case, this is like our, this right here is like our yn. And so that convergence implies this, the convergence of an. All right, and that's only true because Bn converges, right? So this is Bn converges if and only if 3L over 2, since that's a constant, times Bn converges. And then that implies that we have series An converges because of the inequality of 0 less than An less than 3L over 2 times Bn. All right, so we've shown for this, we've shown that Bn converges implies An converges. Okay, now I'll show, use a different color. Now I need to show that if An converges, then Bn converges. Okay, and here, so I'm gonna, again, so I'll assume An converges. Note that for this part, I have this. Note 0 is less than L over 2 times Bn less than An. And so if An converges, the series of An converges, then that means the series 3L over 2 times Bn converges by comparison test. Well, then if that converges, if the series of L divided by 2 converges, you could factor out the constant in front. So then this converges. And then that's if and only if the series Bn converges. All right, so now I've shown the other direction. So we've shown that the series Bn converges implies that, so this time we've shown the convergence of the series An implies the convergence of the series Bn. All right, so I have this and that, so that takes care of the if and only if. All right, so it was a clever choice for epsilon. So again, our sequences A and B are strictly positive. And we're trying to show that the limit A(n) divided by Bn equals L, or equals L if and only if for all epsilon greater than 0 that exists at capital N, that's a natural number such that for all little n bigger than capital N, we have that the absolute value of A(n) minus L is less than epsilon. We already know that's by definition of convergence of a limit of a sequence. And we're taking care of the case of L being greater than 0. So if L is bigger than 0, then L divided by 2 is bigger than 0. And we chose epsilon to be L over 2. And that gave us this inequality. And we use this inequality to establish the if and only if part, where the series of An converges if and only if the series of Bn converges. The first part we showed that the series An converges by making note of the inequality of An less than 3L over 2 Bn. And so if the series Bn converges, then the series 3L over 2 times Bn converges. 3L over 2 times Bn is bigger than An. So the convergence of that implies the convergence of An. Then we use the other inequality where we had L over 2 Bn less than An. So if An converges, it's bigger than the sequence An for the nth term is bigger than the nth term of L over 2 Bn. And so since that's the case, so if series An converges, that means the series L over 2 times Bn converges. Well, if the series of L over 2 times Bn converges, that would imply if and only if the series Bn converges. So that took care of the other direction. When we assumed series An converges, that implied series Bn converges. All right, so that's the proof. I did work it out here, but it's pretty much everything I just said. Okay. All right, so that's the proof where L is greater than 0. Now, if L is equal to 0, then we need to prove that the convergence of series of Bn implies the convergence of the series An. So if L is 0, I'm just going to pick epsilon to be 1. All right, so here's the proof for the case when L is 0. So we know the limit of An divided by Bn is equal to L. And we know by definition of convergence for a limit, that means for all epsilon bigger than 0, there exists some cutoff index capital N, so that for all little n bigger than capital N, we have that the distance between An over Bn minus L is less than epsilon. So we know that. So since that happens for any epsilon, let's fix epsilon to be equal to 1. Since we know it converges, to find the necessary capital N, so that for all little n bigger than capital N, we have that An over Bn minus L, which since L is 0, that's just the absolute value of An over Bn being less than 1. That's if and only if we have -1 less than An over Bn less than 1. We know An and Bn are strictly positive. So then for all little n bigger than capital N, we have -1 less than 0 less than An over Bn less than 1, right? Because they're both a positive divided by a positive can't be negative, so we only consider when it's in between 0 and 1. Then if we multiply this by Bn, we have 0 less than An less than Bn. So by the comparison test, if the series Bn converges, that would imply the series An converges. Since the sequence of the nth term, so for the nth term of Bn being greater than An, that meets that requirement for convergence for the comparison test. All right, so that's the limit comparison test and the proof of it. So here are just some special series. I don't really go into proofs of these. Just went ahead and just list them. So we have the telescoping series. Essentially, it's just a series where you have the terms such that you have like B1 minus B2 plus B2 minus B3 and so forth. And so we have something of that pattern. And so for the nth partial sum, so nth partial sum, we see that the values B2, negative B2 cancel with positive B2, negative B0 cancel to positive B3, and so forth. And then you'll have a negative Bn cancel with the positive Bn. So that leaves us with Sn equal to B1 minus B subscript n plus 1. All right, and so we take the limit. So this limit of Sn, that's going to be the limit of this difference. B1's a constant, so that's equal to just B1 minus the limit of the n plus 1 term. And that might involve some value in. All right, and that's what that would be. As far as what the limit is of the sequence of nth partial sums. Then we have the P series, and that's just this series of the format 1 over n to the P power. So that's like 1 over 1 to the P plus 1 over 2 to the P plus 1 over 3 to the P dot dot dot, and that only converges when P is greater than 1. So like the series 1 over n squared to P series, P is 2, greater than 1, so this converges. But the harmonic series 1 over n, that has P equal to 1, that's not less than 1. So it diverges, but I'll show in the next video a better proof than they're saying it's a P series with P equal to 1. We already talked about it, but there's the geometric series, which we proved earlier for absolute value of r less than 1, that you get a over 1 minus r. Then there's the alternating series. An alternating series test is if you have some series of the form -1 to some exponent, let's say it's n plus 1, and then times some sequence an. If that sequence an is monotone decreasing and it converges to 0, then the series converges. Okay, so that's different examples, or sorry, the theorems and such that we will go over for this part of the course. Depending on the time, we might go back into like series more, into power series and series of representations of functions using power series. Okay, so the next video, I'll go into some 6 examples and how to apply the information that we learned to answer these 6 examples.